Hey folks, welcome back. This is the first video in a three-part series on topological data analysis, or TDA for short. TDA is an up-and-coming approach to data analysis that focuses on looking at the shape of data. This first video will serve as a brief introduction to the topic, setting the stage for the next two videos, which talk about two specific techniques, the mapper algorithm and persistent homology. So without any further ado, let's get into the video. So starting place for all this is the observation that data volumes across different domains seem to be increasing at an accelerating rate. And in many cases, this is a good thing. For example, it served as the fuel for so many of the technological innovations in the past decade or so, like image search or recommendation systems, natural language processing, and so on. But there's a problem. Mo data often means mo problems. And any practitioner will tell you data from the real world is often noisy and high dimensional. And so that's where topological data analysis, or TDA for short, can help. And the catchphrase for TDA often goes something like, data has shape and shape matters. So the basic idea of TDA is to take data and translate it into some kind of shape. So the reason this is helpful is that the underlying shape of our data is often much more robust to noise and perturbations that our data generating process may undergo. And additionally, all the TDA algorithms that extract shape from data, at least the ones that we will discuss in the series, are readily applicable to very high dimensional data sets. So all in one package, we can both handle the problem of noisy data and high dimensional data with this single framework of topological data analysis. So the first keyword in the acronym TDA, topological, comes from the mathematical field of topology. And the story of topology goes back to a famous problem called the Seven Bridges of Königsberg. And so Königsberg is an old city which looks something like the image we have here on the left. So Königsberg can be described as these four land masses sitting to the north, south, east, and in the center, connected by seven bridges. And that's what's being shown in this image here. And so the famous problem goes something like this. What path crosses all seven bridges without visiting a single bridge more than once? So I'll try to say that again in different words. So is there a path on this map of Königsberg where we can cross all seven bridges but only visit each bridge a single time? So if you want, you can take a moment to try to find such a path, but it would be futile because no such path exists. It's one thing to say it, but to demonstrate this mathematically took the work of a very famous mathematician, Leonhard Euler. And so the way Euler solved this problem is by drawing a picture of Königsberg. But not like the picture we see on the left here. The picture that Euler drew was much more simple. And it looks something like this. It's just a collection of circles connected by lines. And today we call this type of picture a graph. And we call these circles vertices or nodes. And then we call these connections between nodes edges or links. And so what this graph is representing is actually Königsberg, where each circle corresponds to a landmass in Königsberg, and every line represents a bridge. And we have two circles are connected by a line if the corresponding landmasses are connected by a bridge. So what Euler did in drawing this picture, drawing this graph, is he boiled down this map of Königsberg to the essential elements, which eventually allowed him to solve this problem. So what Euler did all those years ago is basically what we're doing when we do topological data analysis. So we take data, we can consider this map of Königsberg as data, and we want to extract the fundamental shape of this data. So as you can imagine, there are countless ways in which we can take data and translate it into its underlying shape or structure. So in other words, there are a lot of ways in which we can do topological data analysis. So there's this very nice review article by Chazal and Michel. I probably butchered those names, so I apologize, but the reference is given here at the bottom. So in this article, they describe a generalized pipeline for topological data analysis. It goes something like this. So you start with your data, you translate that data into some shape, some underlying structure. It could be a graph, just like Euler did, or it could be something else. And from that shape, you extract topological features. Then you can use those features to inform analysis, which can range from just basic statistics all the way to very sophisticated machine learning models. So the motivation for this series is that when I was first exposed to topological data analysis, it was really exciting. I would see these really cool and engaging visualizations applied to a very diverse set of problems, such as discovering new subtypes of cancer, or defining new roles based on basketball statistics, or even describing the evolution of politics in the United States. But then the problem came when I started to dive a bit more into the details of topological data analysis, and I was met with this, a wall of terminology and jargon, which isn't a bad thing. The mathematical rigor associated with topological analysis is a good thing. A lot of the techniques under the umbrella of topological data analysis are very well founded mathematically. But as a non-mathematician, as an outsider, so to speak, trying to figure out what's going on here, there was just a barrier to entry to use this stuff in practice. And so my goal in this series is to put the terminology aside to a large extent and focus on two main goals. One, I'd like to highlight key ideas from topological data analysis for non-mathematicians. And two, I want to share ready-to-use example codes that showcase what topological data analysis can do. So in the next two videos, I will be talking about two specific techniques, respectively. The first technique is called the mapper algorithm. What this algorithm provides is something very similar to what Euler did. We will take any generic data set and we will translate it into a graph. Then in the following video, we will discuss another specific technique under the umbrella of topological data analysis called persistent homology. So I hope you've enjoyed this video. If you'd like to learn more, check out the resources provided in the video description. If you found this video helpful, please consider liking, subscribing, or sharing your thoughts in the comments section below. And with that, thanks for watching.